Hello everyone, welcome to the fourth lecture of this fifth module where we are discussing humidity and chemical sensors. In our discussion, we have reached to the point where we started talking about gas sensors. We have seen different type of gas sensors in brief, in which we have seen that a sensor which changes its resistance in presence of chemicals, particularly gases, we call it a chemi-resistive device, very similar to this, where you have pattern of this metal, say it is platinum or gold or say palladium. Okay, these kind of metals are used, and this is patterned like a comb on a ceramic substrate. Sometimes it is also patterned on a silicon oxide substrate. In that case, you have to be very careful that like platinum do not have a very good sticky nature on SiSiO2. So for that case you have to look for some other material like say titanium. Titanium has a very good adhesive nature on SiSiO2 substrate. So usually this comb kind of structure is deposited something like this, say 10 nanometer thickness of say titanium. On top of that, say 90 nanometer of platinum. Okay, so this kind of configuration is used in practical sense for this IDs, interdigitated electrodes, for gas sensing application. Similarly, if you want to have a gold contact, usually we have 10 nanometer thick of chrome or chromium and say 90 nanometer thick gold. Okay, because this chromium will increase adhesiveness of this metallic film on the SiSiO2 substrate. Okay, so this is the comb electrode, this is the ceramic substrate, and this is the two terminals where you are going to probe your device. Okay, this is chemi-resistive device where this film, this sensitive film usually made up of some semiconductor. Okay, this is a semiconductor material which is the receptor for this kind of device. Okay, changes its resistance when it comes in vicinity of a toxic gas. Okay, this is the chemi-resistive device. Then we have piezoresistive piezoelectric sensors where you detect the change in mass of say quartz crystal microbalance or any other film. Okay, then you have electrochemical sensors. Electrochemical gas sensors are very popular, very similar to the chemi-resistive devices, which are also very popular. So the basic structure of electrochemical sensors are something like this. You have a capillary diffusion barrier. A hydrophobic membrane is used to filter out any kind of water vapor to enter into this. We also call say gas membrane. Okay, this is a gas membrane through which the toxic gases can permeate. Okay, this is gas membrane. Okay, then you have three electrode structure. In the chemi-resistive device, you have seen that there are two electrodes. One is this comb and another is this comb. Okay, here you have three electrode kind of structure, where the first electrode is known as, this one is known as sensing electrode, or sometimes also known as working electrode. Okay, then you have a reference electrode and you have a counter electrode, and everything is inside a electrolyte. Okay, what happens is this gas molecule will start some oxidizing or reducing reaction, or oxidation or reduction at this sensing electrode, or we call it working electrode. Okay, and due to this reaction there will be a generation of some electron. Okay, and this counter electrode completes this path of the electron. So you have a complete circuit. Okay, and you have a electron flow. So this gas molecule which enters into this hydrophobic membrane starts a reaction at this sensing electrode and triggers a electron flow in the circuit. Okay, then you have a reference electrode, which is of course optional, but it is very crucial sometime to maintain the potential at the sensing electrode or at working electrode, or to balance potential at the working electrode. Okay, usually these electrochemical sensors are based on change in EMF or electric current. Okay, mostly these devices are linear with the change in current. Okay, then you have field effect transistor. Of course, this field effect transistor is just one part. You can have a number of transistor, basically gas sensors based on 3-terminal devices. Okay, so you have basically a field effect transistor in place, but here you are not doing any kind of computing with this transistor. Okay, but what you are doing is you are using it as a sensing device. Okay, usually these devices work on the basis of changing the work function. Okay, but there are other ways also to characterize, for example, change in the channel current of this device. Okay, so all of you know about a field effect transistor. The basic construction of a field effect transistor is something like you have semiconductor, then you have a oxide, on top you have a metal which acts as a gate, and then you have a source and drain, right? So very similar structure is shown over here. Okay, and then you have a channel material. So this FETs can exist in several ways. You can have backgated field effect transistor, you have all around gate field effect transistor, and FinFET. There are number of configuration. Okay, but the idea remains same, that what we are doing is we are trying to measure the change in the work function or change in the channel current of this FET. Okay, then we have capacitive gas sensor, where mostly this insulating materials or dielectric materials are placed between two plates, and with the exposure to some gas molecule, the dielectric property of this film changes. Okay, and based on that you have change in the capacitance. Okay, and that is measured in terms of, say, change in the charge or change in the voltage. Okay, that's how capacitive gas sensors works. For optical gas sensors, there are a number of opportunities where someone can tap its property. Okay, so a optical gas sensor can be based on change in reflection, it can be based on absorption, it can be also interferometry kind of device. Using its fluorescent properties, some of the material has been reported as a excellent fluorescent gas sensors. There are some material which changes its refractive index when it comes into comes in contact with a toxic gas. Okay, so those devices can also be made where you have actually the change in refractive index in presence of gases. They are actually very popular. Okay, then optical path length change with the absorption of the gas is another phenomena which has been cultivated for development of optical gas sensors. Okay, now we understood the all of transduction phenomena of the gas sensors, but let's also understand that how these devices has evolved. Okay, that is very much necessary to understand. And all this sensors started with catalytic sensors. Okay, catalytic gas sensors were the initial ones which has been developed to measure toxic gases inside coal mines and other places where people were dying because of suffocation and because of breathe and other issues. Okay, the combustible gas mixtures burn when they attain a certain ignition temperature. We know. Okay, be it methane or be it hydrogen or any other gas. Okay, the gas will begin to ignite even at lower temperature in the presence of particular chemical process. So you can fasten this process if you are using some catalyst or even under high pressure. Okay, you can have different conditions where this explosion temperature can be brought down. Okay, usually catalysts were used in this catalytic sensors to bring down the temperature of explosion for these sensors, these gases at trace level. Okay, so for example, if I have 1% hydrogen, okay, or say 1% methane, okay, CH4, it catches fire at say 400 degrees Celsius, okay. What I will do is, I have some material, I am not naming it right now. Say I have a material X. If I add a little bit of platinum or say some other noble metal here which acts as catalyst, okay, this temperature at this surface will be very less. Say it may be 300 degrees Celsius or so, okay. So by using this catalytic properties, this catalytic sensors has been developed, okay. So the gas sensors based on the catalytic combustion principle is called catalytic gas sensors, okay. The oldest catalytic gas sensors were nothing but a coil shaped platinum wire, okay. Just what people started exploring is using simply a coil of platinum. They started to find that, okay, they were able to detect some gases, okay. So this was used to produce an efficient heating and a strong signal for a gas sensor, okay. Though the platinum has excellent properties, but it is a poor catalyst for combustion of most of the hydrocarbon gases, okay. So for the detection of hydrocarbons, the required temperature was very high. Very high means anything above 900 degrees Celsius or so, which is actually very difficult to attain if you are not relying on electric heating, okay. If you are doing some, you are subjecting this coil to some external heat, from that attaining this 900 degrees Celsius to 1000 degrees Celsius is very difficult, okay. So at this temperature, the platinum starts to even evaporate, and as such the resistance of the platinum wire increases, okay. So what happened, you know that this metallic wires are having a positive temperature coefficient, right? So its resistance increases with the rise of temperature, okay. So what happen is, when you attain a temperature of 900 degrees Celsius or 1000 degrees Celsius from room temperature, what will happen is its resistance is going to increase like anything, okay, and at 1000 degrees Celsius it will partially try to evaporate, okay. So then, I mean, it cannot be called as a good sensor, because after some time there will be no receptor material, right? Because here the platinum coil itself is acting as a receptor, okay. So what is the solution? Okay, the solution is, they found is was the to coat this platinum with some metal oxides and finally treat this as a sensor. So metal oxides, you know that it has a much higher boiling point or evaporation point. Therefore, these coatings can help to keep this platinum and it stops the evaporation of platinum. Okay, so this coating is to be done with a catalyst like platinum, palladium, or thorium compounds. Okay, so very similar to this, you can see that this is metal oxides coated on the platinum wire. Okay, a catalytic bead kind of sensor where the metal oxide coating is there. This coating makes the sensor more rugged, more stable, and resistant to shock and vibrations, because metal oxides are really stable compounds. Okay, the micro hot plates have been widely used in gas sensing in place of platinum coil due to its higher power consumption. Okay, this type of sensor contains a catalytic surface coated on a hot plate with a platinum resistor. So very similar to so this was a coil kind of structure. Now what I am telling you is, I have a plate, okay, on which I have patterned a platinum. Okay, so here it was a 3D structure. Okay, this is in 2D where it is coated on a, this platinum is patterned, on say silicon or SiO2 or any say ceramic substrate. Okay, and you can see this as a top view. So you are seeing a 2D view of the platinum wire. Okay, so this kind of platinum can heats up the catalyst to a very high temperature at which any flammable gas molecule can ignite. Okay, the concentration of gases can be detected by monitoring the resistance change of this platinum resistance arising from the increase in temperature. So when you increase this temperature, the gas will ignite, okay, at the surface of this platinum, and because of that the resistance of this platinum wire will change, and you can detect that by calibrating it against a standard sensor. Okay, so this is a conventional semiconductor gas sensor where you have a ceramic tube through which a heater in the form of this coil, maybe a platinum or tungsten, is put. Okay, and on top of that you have a sintered semiconductor metal oxides. These leads are the electrodes that you have seen. Okay, this will act as a point where you will take the resistance or you will give any kind of biasing. Okay, but if you see, these structures are really bulky, and if you want to integrate it with the current CMOS technology, it is not possible. Okay, so what people has done is they have come up with the MEMS type of gas sensors. So this is a micro nano gas sensor chip, a typical micro nano gas sensor chip made using etching of a silicon wafer. Okay, if you see, this small structure has 5 different layers. The initial layers, on top of it is a sensing material, which is your receptor. Okay, this can be a metal oxide. Okay, this can be a metal oxide. Okay, anything like zinc oxide or say tungsten oxide or any other oxide. Okay, this metal oxide receptor is patterned on top of some interdigitated electrode or IDE. So this IDE is the second layer. This is my first layer. My second layer is the interdigitated electrode, which is nothing but a patterned electrode. So this patterned electrode is actually patterned on a insulating layer. So I have a SiO2 layer. Okay, beneath it I have a platinum heater which will provide me the temperature at which optimal adsorption and desorption takes place at the sensing material. Okay, so usually this MEMS type of sensors works very similar as compared to this conventional semiconductor gas sensor. I have already described that these sensors work at elevated temperature, particularly to facilitate the adsorption and desorption at its surface. Okay, similarly this kind of device also work at elevated temperature, where this platinum heater provide the sufficient temperature. So you do not have to heat this chip externally, right? So this platinum heater, which is just patterned beneath this insulating layer, can provide sufficient heat for this sensing layer. And all of these layers, this first layer, second layer, third and fourth, are supported by this supporting layer, right? So 5 level of integration is possible on a single micro nano gas sensing chip. Okay, so you have a sensing material, IDEs, insulating layer, heater, and a supporting layer. Okay, then this catalytic gas sensors are usually that we are discussing, the initial ones. Okay, MEMS one I have discussed is the advanced version of what we have seen in case of conventional semiconductor gas sensors, but we are still discussing the conventional sensors, where we were discussing the catalytic gas sensor. The catalytic gas sensors is divided into 2 different types. The first is the pellister type of devices, and second is the thermoelectric type. Okay, so let us quickly understand this pellister type and thermoelectric type before we actually jump into the modern gas sensing devices. Okay, so this is a typical pellister type catalytic gas sensor. Okay, which consists of 2 platinum coil having 2 different functions. We'll come to that, but as the name suggests, this pellister contains 2 words. One is pellet and another is resistor. Okay, so it is kind of measurement of the resistance of this pellets, okay, which is of course changing in presence of some gas molecule. Okay, so the we were discussing the function of the two different platinum coils. Okay, the first coil, both the coils actually acts as a heater as well as resistance thermometer. Okay, so you might be knowing that most of the RTDs, resistance thermal detectors, are based on platinum wires. Okay, so this two coils of this platinum acts as both heaters as well as a resistance thermometers. Okay, this kind of device, if you see this pellister kind of device, okay, it includes two beads. One is active bead, I am calling it a sensing element, and there is another bead which I am calling a reference bead or a inactive bead. Okay, the active bead, this one, okay, is activated with catalyst composed of metals such as platinum or palladium. Okay, the inactive bead doesn't contain any catalyst but serves as a compensating element. So you have a active bead which is of course sensitized with some catalyst, and the reference bead is not sensitized. Okay, but please note that you still have a platinum wire present there. Okay, so a voltage supply powers the circuit and heat up the coil. Okay, depending on the target gas, it raises the temperature of the bead to a range of 300 degree to 500 degrees Celsius, and we are talking still about this active bead. Okay, so because of this rise in temperature, since gases are all around, the gas will ignite, okay, which leads to an increase in the temperature of the detector coil. Okay, so if the temperature around this active bead rises because of this gas ignition, of course the resistance of this platinum wire will change. Okay, so this causes the gas to ignite, leading an increase in the temperature of the detecting coil. Okay, so the increase in temperature raises the coil's resistance, because I have mentioned that this is a metal and metals have a positive temperature coefficient. So if you see for semiconductors, it should be just opposite to it. Okay, so mostly you will find that semiconductors have negative temperature of coefficient, means when you increase the temperature, the resistance of the semiconductor decreases. Of course, this is not always true and there are exceptions, particularly for a single semiconductor there can be some reason because of scattering and other factor, it also acts as a positive temperature coefficient. But for this part of this course, let's understand that metals are positive temperature coefficient materials and semiconductors are negative temperature coefficient of materials. Okay, so the increase in temperature in the region of active bead, what it will do is it will try to increase the resistance of the coil, which will result in imbalance in the Wheatstone bridge voltage. If you see this configuration, it's a Wheatstone bridge circuit. Okay, so because of, if you see this in terms of the resistances, this two resistances R1 and R2 and R0 are fixed, but you have a sensing resistance or the active bead whose resistance is changing if there is some gas ignition. Okay, so if there is a change in this resistance, there is an imbalance in the Wheatstone bridge. Okay, and can be detected as any variation from the null for the galvanometer which is placed in the Wheatstone bridge. Okay, the sensor's output is taken across the Wheatstone bridge circuit. Okay, so this is how a simple Peltier kind of device works. Okay, then we have seen that there is another kind of catalytic sensor which is based on thermoelectric principle, or we call it thermoelectric gas sensor. So thermoelectric gas sensor, as any other thermoelectric device, works on Seebeck effect. Okay, so the Seebeck effect occurs when there is a temperature difference between 2 points in a conductor or semiconductor, and this generates a corresponding voltage difference. Okay, what I am talking about is the junction of two dissimilar materials, okay, two dissimilar metals or two dissimilar semiconductors, okay. So when two dissimilar materials like I call it metal A or metal B, okay, are joined at a junction, at two junction. So I have say a metal A, okay, and another metal B, okay, this is B, okay, these two are joined at these two junctions A and say this I am calling X and Y, okay. These are two different metals, they are joined at X and Y, okay. Please note that if you keep the junction temperature of X and Y at different temperature, say if junction temperature of X is at T2 and this Y is at T1, where T2 is greater than T1, I will call this T2 a hot junction, alright. This junction Y is called say cold junction, okay. So when two dissimilar metals A and B are joined at say junction X and Y, okay, and one is at higher temperature and one is at lower temperature, what will happen is a voltage will develop between the two materials, okay. This happens because the charge carrier in the materials diffuses from the hot side to the cold side, creating a potential difference, okay. The amount of voltage generated depends on the Seebeck coefficient of the material used and the temperature difference, okay, and this is known as the Seebeck effect, okay. I mean, thermoelectric gas sensors are based on the Seebeck effect, okay. So Seebeck coefficient is nothing but voltage generated divided by the temperature difference between the two junctions. So if the hot junction is at temperature T plus delta T and cold junction is at temperature T, the Seebeck coefficient can be defined as V by del T, okay, where V is the voltage generated and delta T is the temperature difference between the two junctions, okay. Now the thermoelectric gas sensors are based on this, okay. So you have two different thermopiles. One is say I am calling this layer as a thermopile, okay. This layer I am calling also a thermopile, okay. This layer is nothing but thermopile layers, okay. You have a catalytic thermopile and a reference thermopile, okay. This gas will interact at this point, okay, and it will generate output this del V, which is equal to N into S into del T, where this is the temperature that we have seen, S is the Seebeck coefficient and N is the number of thermocouples in the thermopile, alright. So this is how a thermoelectric gas sensors work, alright. So I hope that the catalytic gas sensors is clear to you, okay. The operation of Peltier gas sensors and thermoelectric gas sensors are pretty much clear. Still these thermoelectric gas sensors are being discussed in the, and of course it has limited applications, not very common as electrochemical gas sensors and say chemiresistive gas sensors, but yes, they have significant presence, particularly for specific applications, okay. In the next class also we will continue our discussion on these gas sensors and we will try to finish this module 5. Thank you.